All right. So when you add vectors, the phrase, if some of you may have taken a physics class and maybe be familiar with this, is we use head to tail. Graphically, it's really easy to add vectors numerically. Like right now, I'll just go ahead and we'll go ahead and add these two together numerically, and it's really easy, but you also need to be familiar with what's going on graphically. So I've got my two vectors here. And well, for one thing, it kind of makes sense is that hopefully, we can talk about two-dimensional where you just have basically an X and a Y and then, three-dimensional vectors. And in reality, vectors can go beyond 3 dimensions. Even though we can't graph it, we could still talk about something that has like 4 parts to it or 5 parts to it. But it would make sense if you were going to add 2 vectors, they should be the same size, right? This should be a 2D one, this should be a 2D one. And what makes sense then is the X component of each of these is 2 for A and 1 for B. So what I should just do is add the X components and then add the Y components. And that will give me the vector 3, 4. So it's really easy to add them numerically. What's going on graphically, though, is if we plotted vector A, let's start from the origin, that vector goes 2 units in the X direction, 1 unit up, 2, 1. So here's vector A, if I plot it from the origin. And then what happens is if I want to add vector B to that, looks like I used uppercase B, so I'll make this an uppercase B, which is the vector 1, 3. That vector, of course, if I plotted it from the origin, you would go over 1, up 3. But if we're going to add it to this, then we just pretend where we left off with vector A, pretend that's the origin. And you're going to go over 1, up 3 from here. Over 1, up 3. Here's vector B. And the way it works is the sum, this vector 3 plus 4 is the vector from where we started this whole process to where we ended up. So this would be the vector A plus B. So that's how we're adding 2 vectors. Because yeah, I could see like on a final, whoops, someone's coming in. There we go. I could see, you've got lots of practice adding them numerically, but then I could see certainly like here's vector A, here's vector B, sketch A plus B, right? So you have to know how to add them graphically as well. Yeah, and these terms keep coming up. A vector, well, let me start with a scalar. A scalar can be thought of as just a number, whereas, which could also be thought of as, or magnitude. Whereas a vector, it has 2 things, right? It does have magnitude, but it also has direction, magnitude and direction. And so a good example for each of these is, the classic example is velocity is a vector in that, if somebody said they were in their car going negative 10 miles per hour, what do you think that the 10 is a magnitude, right? 10 miles per hour is a magnitude, but what do you think the negative implies? They're probably going backwards, right? They're going backwards, going in reverse. So there is a direction implied with the negative. Whereas if for that same person, if they were driving backwards in their car, if someone said, what's their speed? Speed is a scalar. We would say their speed is 10 miles. No, I don't want that to look like a negative. Their speed is 10 miles per hour. Okay. So when we talk about speed, we don't usually indicate which direction you're going. It's just, in fact, speed is the magnitude of velocity. Speed is a scalar. Velocity is a vector, can be thought of as a vector, even though we don't write it like this. We can in physics. When we get to physics, you can. But because of that negative sign, that implies a direction. So just I want to mention that. And so what about the vector if I wanted to do 3a plus 2 times b? This would be, you could describe this as a scalar times a vector plus another scalar times a vector, right? When you think of scalar, you can think of a number or a constant. Again, numerically, this is really, really easy. 3 times vector a would be 3 times the vector 2, 1. And when you multiply a vector by just a constant, you can literally just distribute the constant. That's going to give you 6, 3. And likewise, if I did 2 times vector b, that would be 2 times 1, 3, which is 2, 6. And what's going on graphically, I'm going to draw this a little bit, this is going to kind of get kind of big if I add these. Oh, well, let me find out what the sum is, first of all. So if I did 3a plus 2b, that would be like adding these two right here. So that's going to give me the vector 6 plus 2 is 8. 3 plus 6 is 9. What's going on graphically, though, I'm not going to draw a scale here, but 3a means you're basically taking, you know how vector a kind of goes off in this direction. You're taking 3 of those, 1, 2, 3 of those. That would be like 3 a's, right? And then you're adding 2 b's. So b kind of goes off this direction. You're going 1 and then another one on top of that. This is your 2b. So that vector 8, 9 that we're getting is again just the sum of those. It's going to take you from where you started to where you ended up. And then the deal with subtraction is if I want to take vector a minus vector b, I can always think of this as vector a plus the negative of b. And let's do the graphical part first. So vector a, if I start at the origin, I'm just going to again just estimate I'm going to draw it bigger because I have a little more room. That would be going off in this direction, right? That's 2, 1. And positive b, as we saw, would be a vector that goes over this direction. This is positive b. And what the negative of b is you just take that vector and you flip it around. It's going to go the opposite direction, right? Kind of like negative 10 miles per hour. You're going to go the opposite way. So negative b, here I'll go back to blue here, would be going this direction. And so I'm going a plus the negative of b. So my final result would be right here. This is the vector a minus b. Numerically, it's really simple, right? You just subtract the x component. So that's going to give you 1. 2 minus 1 is 1. 1 minus 3 is negative 2. So it's really easy to get that. Answer numerically. Okay. And then one other thing I wanted to review, this was kind of from Friday, but it's such a big point and it comes up in some of the things we do with the dot product as well. So I wanted to do just a quick review of this. Say I have this 3-dimensional vector A, 2, 2, 1. So that's x, y, and z now. And the directions here say find a vector of length 7 in the same direction as this vector. Now it gets much harder to plot 3-dimensional vectors. So most you wouldn't be expected to, I doubt, to plot a 3-dimensional vector. I could show you This one isn't too hard because I made them all positive. So maybe I will show you just for this, but don't worry about graphing them in the future. I don't think you're going to have to do this, but what the vector 2, 2, 1 would be, remember how we were plotting points? And if you started at the origin and went 2 units in the x direction, 2 units in the y direction, so you went here, then you went here, right? And then you went up 1 unit in the z direction. There's no way to change that, is there? That's okay. 1 unit. So from here, that might take you, I'm gonna really exaggerate on the z-axis. Let's call this 1/2. Let's call 1 like this. Let's say I have a different scale here because I want you to, you're not gonna see it if I put it right here. Probably wouldn't have been that high, but that's okay. Let's pretend this is my point, but hopefully you get it. You went over 2, and then up 1. I just made that look extra big. And I remember when we were graphing in 3D before, I kind of made like a little box around this, so you could certainly do that. Good enough. Okay. But the vector 2, 2, 1 would be a vector that starts at the origin here and goes straight to this point 2, 2, 1. So it's a 3-dimensional vector coming out. It has an x component, a y component, and a z component. Okay. Now the directions say to find a vector of length 7 in this same direction. So maybe we ought to figure out what is the length of A, because if the length of A is 7, then we're done, right? It's already in the same direction. And the length, remember in vector notation or terminology, that's what we refer to as the magnitude. So the magnitude of A, and then, yes, you just have to know now, if someone gives you a number and they say the absolute value of -5, well, that means absolute value. But if someone puts an absolute value around a vector, that means something different. That means the magnitude. And it's basically based off the Pythagorean theorem, where you're just going to go 2 squared plus 2 squared plus 1 squared. And that actually gives me 4 plus 4 plus 1, 9. So I get root 9, which is equal to 3. So we know that vector A has length 3 right now, and they're asking us to find a vector that's going in the same direction. Okay, now we know this is length 3, but we want it to be longer, right? We want the length of this to be 7, right? We want the total length to be 7. So there's a couple ways to think about it, but this is the way I want you to think about it. This is the value of making something a unit vector. How I'm going to find this vector is I'm first going to find a unit vector in the direction of A. And remember, all a unit vector is a vector that's pointing in the same direction as A, but only has length 1. So I'm going to effectively shorten down my vector A to length 1, and then I'm going to multiply it by 7 so that it has the correct length. Okay, so first I want to make it a unit vector, then I can stretch it out to whatever length I want by just multiplying by that number. So I'll put unit vector in the direction of A. How I find that, remember, is you just take A divided by its magnitude. So I take vector A, which was 2, 2, 1. We just found out the magnitude's 3. And what you can do is distribute the 3 evenly into all 3 of those. So you'd get 2/3, 2/3, 1/3. Apologize, I'm getting a message that my it's been acting up the last few weeks, saying it's unstable, but we'll see. So again, this magnitude, that's what we mean by a unit vector. The magnitude, I'll just put MAG for this, is equal to 1. That's 1 unit long. That's this vector here. So now multiply it by 7. I'll put quote unquote stretch it out, meaning multiply by 7. And so 7 times my unit vector is 7 times 2/3, 2/3, 1/3. Gives me 14/3, 14/3, 7/3. Now I have the correct direction and length. Any questions on that? So unit vectors are really important because if you make something a unit vector, the direction is preserved. You have it as length 1 and the direction is the direction you want it to be in. And then you can just multiply it by whatever length you want your vector to be, right? Because you're just multiplying it by 1 basically, right? Okay. So you already saw the dot product formula. We'll go through this pretty quickly because I think this part's pretty easy. If you've got 2 vectors, we'll go ahead and use the two three-dimensional vectors as our example. The dot product is as simple as, for my vectors, I have C, D, E, and F, G, H. You're just multiplying the X components and then adding the product of the Y components and then the product of the Z components. It can be that easy. You should already have this formula or something equivalent to it in your notes here. So for example, vector A, 2, -1, 3. If I want to dot that with vector B, 5, 3, -4, it's just going to be 2 times 5 plus -1 times 3 plus 3 times -4, 10 minus 3 is 7. This is minus 12, 7 minus 12. So I get a dot product of -5. Okay, so, you can do these in your head most of the time, right? I'm writing out what I'm doing here so you see, just make sure we're doing the same thing, but most of the time you just do it in your head. It's pretty easy. But then the question is, what does that mean, right? What are we actually doing when we're finding a dot product? What happens when you do this kind of multiplication with vectors? Coincidentally, I would say, or inadvertently, what you're actually finding is this. If I took my 2 vectors and put them tail to tail now, not head to tail, I'm not adding them, but if I put my 2 vectors tail to tail, assuming they're not going in the same direction, there's going to be an angle between them, which we'll call theta. And essentially what this number means is it would actually end up being the magnitude of A multiplied by the length of B, the magnitude of B, times the cosine of the angle between those two. I'll just put, well, I'm going to give you more meaning to this in a second here. And then you could say, well, Grant, okay, that's what it means, but what does that mean, right? Let me go a little bit deeper into here. What happens is, so I'm sneaking up on a topic which I'm going to talk about later, but you've talked about projections at the end of class today. The way I like to think of a projection of a vector onto another is, here I have A over B here, and if the sun was directly overhead on a bright sunny day, straight up, do you see that A would cast a shadow onto vector B, this shadow right here, okay? This length right here is, in this case, it's actually the magnitude of A times the cosine of theta. It's pretty easy to see that, because if I just do cosine of theta is this over this length, which is the magnitude of A, you'll see and solve for this, it's going to be magnitude of A times the cosine of theta. So the way we can interpret this, and we do this a lot with vectors, is if you have two vectors that are not pointing in the same direction, you can think of one vector, I'll just use A, as the sum of two vectors, one vector that's going in the same direction as V, and one vector that is perpendicular to V. This one's called the projection vector. We'll get more specific with this later on. And this one's actually called the orthogonal vector. I don't think you're responsible for it. It is covered in 8.3, but I haven't seen Dr. Burke talk anything about the orthogonal vector, so you don't have to worry about that. But essentially what it means is A, magnitude of A times the cosine of B. This can be thought of the way I think of this. This is the part of A in the same direction as B. That's what magnitude of A times cosine of theta will give you. And so what's really going on, what the dot product really is it's this length, the part of A that's going in the direction of B, times the length of B, times the magnitude of B. You're taking this length times this length. That's what the dot product is telling you. And you still say, Grant, okay, well, what is that? There's uses for this. I do have one that from the book that I don't know if we'll have time to get to it today, but certainly on Wednesday. Turns out that can have some special meaning. So for example, I just really want people to understand what a dot product is. Let's say I took the vector 3, 4, and I wanted to dot it with vector B, which was 7, 0. And I just kind of did a little plot of this. 7, 0 would just be 7 units in the X direction and nothing in the Y direction. So it's purely in the X direction. And in fact, the magnitude of B, I don't need a formula for that. If it's going in 7 units in the X direction, I can tell the magnitude of B is 7, right? And if I wanted to do A dotted with B, let's just do it the regular way, the easy way. The magnitude of, A dot B, we decided was super easy. You're just going to multiply 3 times 7 plus 4 times 0. My answer is 21. No problem there. And you can't see that, except you can't see it. That's the only problem. There we go. Now you can see it. But let's think about what this is really giving us. Do you see that 3, 4, that vector? I could actually think of that because I have my other vectors purely in the X direction. This vector A can be thought of as you're going 3 units in this direction, right? And 4 units up in this direction. That's how you get to the vector 3, 4 right here. But look at my answer was 21. And what was it essentially? Where did my 21 come from? It came from 3 times 7, which is exactly what I was saying here. 3 is the part of vector A that is going in the same direction as B. It was this length times the length of B, which was 7. That's what gave me my final answer. In fact, this part was just 0, huh? And that's because the part of A that was perpendicular to B is not going in the direction of B, right? It's going perpendicular. So it contributed nothing to the dot product because this part's not going in the direction of B. Anyhow. Knowing that the dot product, while it's easy to calculate mathematically, so now I have 0, 4 for A, 6, 0 for B. I could probably plot those. Okay, you can see 0, 4, if I started at the origin, let's say, that would go straight up 4 units. B would go 6 zeros straight to the right. So we know the angle between those should be 90 degrees. And look at my dot product. What I'm going to get is 0 times 6 plus 4 times 0 is going to give me 0, which totally matches up with my other definition, right? Because I could have also done this. I could have also used the magnitude of A times the magnitude of B times the cosine of the angle between them, but I can already see that that's 90 degrees, and it doesn't even really matter what the magnitude of A and B are because the cosine of 90 degrees is 0, right? This is going to come out to be 0. And so a very, very important thing about the dot product is knowing that if you have two vectors and it turns out that the dot product is 0, then your two vectors are perpendicular. And I think you're starting to see, I don't know why we need so many names for the same thing. Another word for perpendicular is orthogonal. And yet another word for both perpendicular and orthogonal, which I really don't care for, is normal. In the context of vectors, normal means perpendicular, which is, still don't know why anybody would have chosen that word. To mean perpendicular. And it's really valuable. You know, you could probably sketch a couple of two-dimensional vectors and figure out that they're perpendicular because you could evaluate the slope perhaps, right, if you were graphing them. But when you have three-dimensional vectors, it's really hard to see it, you know, if two three-dimensional vectors are perpendicular. And so one of the ways we could tell, in fact, this one's, we don't have the whole vector B, but we're going to try to figure out what X should equal so that these two vectors are perpendicular. And in order for that to happen, A dotted with B needs to come out to be 0. And that's going to lead me to my answer because A dotted with B is 3 times 8 plus 2 times -2 and then plus -4 times X needs to be 0. So this is 24 minus 4. How about I just move that 4x over, equals 4x. So in this case, X needs to be 5. One added bonus, now that we have, I mean, there's two ways to think about the dot product, right? There's the easy way, just multiplying and adding. And then there's sort of what's it really telling us about the two vectors? It's the magnitude of one times the magnitude of other times the cosine of the angle between them. Because we have two ways to evaluate the dot product, we can actually now have the ability, if we want to, we can find any angle between two vectors. I don't think I want to try to plot these. Because, right, because if I have A dotted with B, and I know that one of the definitions is that's the magnitude of A times the magnitude of B times the cosine of the angle between them, right? We'll just assume there's some angle between the two. Well, I already know how to do A dotted with B, right? On the left side, I can work that out. I don't even need to know that angle theta because I know it's just going to be 4 times 1 plus 0 times 2 plus -3 times -2. I know how to find the magnitude of A. That's just going to be the square root of 1 squared plus 2 squared plus -2 squared. Same thing for the magnitude of b. That's going to be the square root of 4 squared plus 0 squared plus negative 3 squared. And the only unknown would be the cosine of theta. So as long as you know this, right, you can just manipulate it, because this is what we'd be solving for here. We'd be looking for the cosine of theta. What do I get here? This is 4. That's 0. 4 plus 6, so this is 10. Oh, this is like one of my first problems. That's 1 plus 4 plus 4. That's 9. This is root 9, which is 3. I'll just put root 9 for now. That's 16 plus 0 plus 9. This is root 25. This is just 3 times 5, so 15. So what I can see here is the cosine. If I isolate the cosine of theta would be 10/15 or 2/3. If I actually want to know what theta is, I would have to get a calculator out and do the inverse cosine of 10/15. I might as well reduce that, 2/3. And just a note on that, you could probably just leave it like that if it was on a test or something as an inverse cosine, unless maybe it was one of the angles you remember. If you know your special angles, you might be able to get that down to an angle, but I don't think you'd need to get a calculator out on a test or anything. The other thing too is oftentimes if you're doing WebWorks homeworks, I haven't seen the latest one, but oftentimes when they say, instead of asking for the angle, they'll say the cosine of the angle between these two vectors. So they might want this as their answer. If they say, what's the cosine of the angle, they might want that. But if you actually want the angle, you have to do the inverse cosine, right? And there's some pretty cool stuff you can now answer that maybe either you've been curious about, or maybe something that, well, I know one application of this one. I should almost change it to that, but it might take longer, so I won't do that. Let's just do this, and I'll tell you the problem that I was thinking of. So this is number 42 in 8.3. Say I have a perfect cube, all sides are the same. And we want to know the angle. So say you were at the origin here. Let's put our cube on the XY axis, and let's just make it a unit cube. So let's say this stretches out to this point here would be 1, 1. I need more room here. 1, 0, 0, sorry. This point right here is 0, 1, 0. This point right here is 0, 0, 1. So we just have a 1 unit cube. This point right here, which would have the coordinates 1, 1, 1. If I drew a vector from the origin to this point, that would be called a diagonal of the cube. Let's call this vector A. We'll come up with a formula for that in a second. But here's an interesting question. If you can envision the diagonal of a cube and then a vector that goes from the origin to a diagonal of the floor of one of the faces right here. Let's call that vector B. There's an angle between those two. What do you think it is? Guesses, let's work in degrees. I know mostly we work in radians and calculus, but I think degrees might be guesses in the chat. What do you think that angle might be? estimates even, I guess, right? And I will say that, yes, 45 degrees is kind of my initial gut reaction of what that angle is. But what if I told you it's not? It's not 45 degrees. Let's do some intuition checking. So if it's not 45, would you be inclined, do you think it's more than 45 or less than 45? This angle right here that goes from, if you think of the cube as like a room, perhaps, like the room I'm sitting in is actually almost like a cube. I assume most people's rooms are more like rectangular, like you don't, remember a cube has to have all of the sides the same. But if you were sitting inside the room, this would be the diagonal across the floor, and this would be a vector that goes from one of the corners to the ceiling, right, of the opposite corner. Well, let's find out. So we're going to need a vector for A and for vector B. Now remember, coordinates here were 0, 0, 0. I think I went over this last time, that if you want to find a formula for vector A, we always just go final minus initial. So it's just 1 minus 0, 1 minus 0, 1 minus 0, which is just 1, 1, 1. Or you can think of it as, if you start at 0, 0, 0, how much do you need to add to x? To get to 1, 1, 1, you need to add 1 to x, add 1 to y, add 1 to z. So there's a couple ways to think about it. Vector B, let's figure out this point right here. This is on the floor, so this would be 1 unit in the x direction, 1 unit in the y direction, but you're not going up. So this point would be 1, 1, 0, which means vector B, final minus initial, 1 minus 0, 1 minus 0, 0 minus 0. Vector B is 1, 1, 0. We're going to need this in the formula, so why don't we do A dotted with B? A dotted with B is 1 times 1 plus 1 times 1 plus 1 times 0. So that's going to be 1 plus 1 plus 0. So A dotted with B is 2. What's the magnitude of A? Magnitude of A is the square root of each part squared, summed together. 1 squared plus 1 squared plus 1 squared. And the magnitude of B is the square root of 1 squared plus 1 squared plus 0 squared, which is root 2. So A dotted with B, we know is the magnitude of A times the magnitude of B times the cosine of the angle between them. We have A dotted with B is 2. Magnitude of A is root 3. Root 2 is B, and then cosine of theta. So if I isolate cosine of theta, this is really root 6, and you would divide it. It's 2 over root 6. And if you actually solve for inverse cosine of 2 over root 6, I had that. Does anybody have a quick calculator handy? Let me see. Because I was curious too. I thought it was, my first guess was 45, and then I'm like, oh, wait, maybe it's not 45. It feels like it should be, but it's not. Let's see, I'm getting in degrees, it's about 35.3 degrees. 30, okay, yeah, someone had it for me. This is about 35. Yeah, it's not 45. It's actually less than that. The diagonal of a cube is smaller than 45 degrees. One of the problems I do with my 21C class, and this might get you thinking here, I'll tell you what, I'll just draw a new picture right here. This is just me having some fun here, but something you might think about. If I had a cube like this, okay, so how many people are taking chemistry? Who's taking chemistry? If I put a carbon atom in the center of the cube, a hydrogen here, a hydrogen here, a hydrogen here, a hydrogen here. What's, no, not there, not there, not there, right here. Put it here. That's a bad place for it. That would not work. Who recognizes that structure? First of all, what molecule is that? No. Have you gotten to this yet? This is methane, right? That's CH4. The CH4 molecule has what structure? I don't know if you've gotten to this yet. Where do they teach that? It's the tetrahedral. Okay, so it sounds like some of you have a tetrahedral structure. And I remember this from my long ago, back in the old days when I was a student. I had to take chemistry too. And there was something called the bond angle, which is the angle between two hydrogens and a carbon, this angle right here. Who knows what that angle is? Because what I remember in chemistry, this is one of my problems with chemistry, was they just told me the angle and I was stuck on that. I was like, how in the world is it that? No, maybe you guys haven't gotten that far yet. This angle for a tetrahedral is 109.5 degrees. Have you learned that one? Okay, yeah, just right when I put it up there. Yeah, remember that one? Yeah. And see, I think that was my problem in chemistry, is I just got fixated on that. And the rest of the lecture, when they told me that in chem, I was like, I was still on, how in the world did they get 109.5? How many people could imagine building a couple vectors here between a carbon and two of the hydrogens and using this formula to find that angle? We actually did it in my 21C class, but the fraction, you end up with fractions, it gets a little more messy. But if you wanted to, you could try it. You should try it just to convince yourself. It does work out. And it can be shown with the dot product formula. Anyhow, a little bit of a distraction, but we may not get to projections today. I might have to save that for the beginning on Wednesday, in addition to whatever the new topic is. But this is, I want you to get this last idea here with the dot product. It turns out that when we talk about equations of planes, flat surfaces, there's a connection between the equation of the plane and a normal vector to the plane. Remember, normal means perpendicular. For whatever reason, when they're talking about planes, though, they usually call it a normal vector rather than a perpendicular vector. So we want to find the equation of a plane, flat surface here. It contains, we know a point on the plane is 2, -5, 1. And they're telling us that there's a vector that's perpendicular to this plane, 3, 1, -2. Remember the idea with vectors. Whatever that vector looks like in three-dimensional space, like my pen, it has a certain length, it has a certain direction. I can move that pen wherever I want to, and it will keep the length and it'll keep the direction. So the idea is this normal vector is some vector in three-dimensional space that I know is perpendicular to my plane. I know it's going straight up at a right angle. I can put that vector wherever I want though. So I am going to put that vector right here. I'm going to put my normal vector right there. And I know it's perpendicular to my plane. And then what I could do is I could pick another random point here in my plane. Let's just call it XYZ, some random point in my plane. And I'm going to get I could generate a vector between 2, -5, 1, and XYZ. Let me call that vector V. And in fact, let's find vector V. Because remember how we do it? This is where I do like the final minus initial. If I start here and wind up here, it's going to be X minus 2, Y minus -5, and then Z minus 1. So that'll be X minus 2, Y plus 5. And here's how we can get the equation of the plane. This vector V is it's in the plane, right? And we know N is perpendicular to the plane. So we know there's a right angle, right, between this vector and this vector. Think about it. Okay, I don't know if you can see this. Let's say my pen is pointing straight up, right, from my piece of paper here. And this green pen is lying down flat on the plane. There's an infinite number of vectors that are perpendicular, right? If my green pen is lying on my paper, it is perpendicular to this. So there's a whole bunch of perpendicular vectors. Since V is lying in the plane, I know that N and V are perpendicular. Since V is in the plane, N and V are perpendicular. Okay. Right at the end of class here, we'll be done when we finish this. Kind of a big summary if you've been paying attention. So somebody tell me what I then know about N and V in terms of their dot product. How many people remember that if N and V are perpendicular, we know that their dot product must be 0. So N dotted with V must be equal to 0. So let's do that dot product. N is 3, 1, not -1, 3, 1, -2, dotted with X minus 2, Y plus 5, Z minus 1. Must come out to be 0. And if I do my dot product, it's 3 times X minus 2 plus 1, and then plus -2 times Z minus 1, so minus 2, must be equal to 0. And in fact, this is the equation of our plane. The equation of a plane usually will have X, Y, and Z in it. We could clean this up. So we could like distribute this 3X minus 6 plus Y plus 5 minus 2Z plus 2. Usually when we write equations of planes, we like to have X, Y, and Z on the same side and all the numbers over on the other side. So we would have 3X plus Y minus 2Z. If I throw all these numbers over to the right side, so if I add the 6 over, subtract the 5, subtract the 2, -1. This is the equation of my plane. And there, just as a last note on this, I don't think this is something you're required to know. This is just more of a kind of an interest thing. And kind of a, what do you call it? Glaring, perhaps coincidence. What do you notice about So this is the final result. This is the equation of the plane. So this plane, I'll write it out. This plane is perpendicular to the vector, which we did was 3, 1, -2. What is kind of interesting about that? 3, I could argue there's a 1 there, -2. What ends up happening, and this is not a coincidence, a little bit counterintuitive to me. What do you notice about the coefficients of x, y, and z in my final answer? They are exactly the same as the coefficients of my normal vector. And so there's this interesting thing about planes is if you know a vector that's perpendicular to your plane, it turns out that the plane itself will have the same coefficients for x, y, and z. I don't know about you, but to me that seems totally not intuitive, but it is, it's true. Yeah. Okay. Yeah, we definitely don't have time to do projections. I'm already over time now. Okay, so I'll work on projections on Wednesday. We'll stop for here for now.